Hey everybody, and welcome to our third pre-calculus algebra lecture. We're going to continue looking at quadratic equations and their solutions. In our last lecture, we considered a quadratic equation of the form x squared minus c squared is 0, the difference of perfect squares. And then we also considered a quadratic equation where we have x squared minus k equals 0, where k is not a perfect square. The next form or special case that we want to look at is ax squared plus bx equals 0. And this is the quadratic equation, ax squared plus bx plus c equals 0, where c, the constant term, happens to be 0. So this is the form of a quadratic equation where we don't have a constant term. And here's how we solve it. We notice that the left-hand side of the equation can be factored. Both terms have a factor of x, so we will factor out the x. And this leaves us with x times ax plus b equals 0. Let's see, did we do that right? X times ax is ax squared. X times b is bx. Yep, we did it fine. Now notice something. We have a product that's equal to 0. The zero factor property, or the zero product property, tells us that one of these factors has to be 0. So either x equals 0 or this factor has to be 0. And that says x equals 0, or let's see, what would happen if we divide both sides? No, tell you what, we'll move the b over here. That's what we'll do. So we'll have ax equals negative b. And that will yield x equals negative b divided by a. And our solution set is 0 and negative b over a. Now, let's get rid of all these letters and do an exercise that has some numbers in it, okay? Here's an exercise that fits the case that we just discussed. A quadratic equation with no constant term. And the one thing that we notice is that we can factor this expression. Both terms have a factor of x, so we factor out the x. Now we have a product on the left-hand side of the equation and a 0 on the right side of the equation. The zero factor property or the zero product property tells us that one of these factors has to be 0. In the first case, we know that x has to be 0. In the second case, we don't know what x has to be yet, so let's solve for x. Move the constant to the right side. And then divide by the coefficient of x. So our solutions are x equals 0 or x equal -2. And our solution set is 0, -2. And typically we'd write this with the smaller constant first, but it doesn't have to be that way. That was pretty easy. Let's do one more. This is a nice one. Again, we notice that there's no constant term on the left-hand side. So the way to go is to factor this expression. Both terms have a common factor of x. Either the first factor is 0 or the second factor is 0. Now, let's solve for x here because we don't have x given explicitly here. Move the constant term to the right side of the equation. And then we divide both sides by 2. These are our solutions. And our solution set is the set containing x equals 0 and x equals 5/2. Next, we'll consider the general case. This is the general case. The squared term is not 0. The x term is not 0. The constant term is not 0. And we're assuming that the left-hand side can be factored. If the left-hand side can be factored, then we factor. We set each factor equal to 0, and we've got our solutions. Let's look at a couple of examples. Here's an easy one to start off with. X squared plus 2x minus 15 equals 0. And we're assuming that we can factor the left-hand side. So this is going to look like x plus or minus something times x plus or minus something equals 0. And whatever goes here and whatever goes here have to multiply together to give us -15. So let's see, I'm guessing 3 and 5. So x plus 3, x minus 5, let's see. 3 times x is 3x. And negative 5 times x is negative 5x. When we add these two together, we get negative 2x. Oops, we got a positive 2x here. So it looks like we have our signs wrong. It looks like maybe what we need is x minus 3 and x plus 5. Let's try that. Negative 3 times x is negative 3x. And x times plus 5 is 5x. Negative 3x plus 5x is plus 2x. Oh, that gives us our middle term. Okay. We did this correctly the second time. We've correctly factored this expression. And what we have is the product of two factors equal to 0. The zero product property or the zero factor property tells us that one of these two factors has to be 0. So we have either x minus 3 equals 0, or we have x plus 5 equals 0. And we solve both of these equations for x. Move the 3 to the right. Here, move the 5 to the right. And these are our two solutions. Our solution set will look like x equal negative 5 and x equal 3. Now let's do another example where we can solve by factoring. Here's one that's a little bit more challenging. 2x squared minus 5x minus 3 equals 0. And we're assuming that this thing can be factored. So let's see what we can do. If the left-hand side can be factored, then we're going to have 2x here and x here. And we're going to have factors of negative 3 here and here. Oh, I don't know how this is supposed to go. I'll try plus 1 and minus 3. Oh my goodness, I think I hit the jackpot on the first try. Let's see. If we multiply these two terms together, we get x plus x. If we multiply these two terms together, we get negative 6x. And that gives us negative 5x, the middle term. Ah, this is correct. You know, I usually don't get these right on the first try. Usually I have to try twice, 3 times before I get the exact numbers to put in here. There's a little bit of trial and error there. Well, we got it right on the first try. Good. Now, what we have is a factor, we have a product equal to 0. The zero product property or the zero factor property tells us that one of these two factors has to be 0. So either 2x plus 1 equals 0 or x minus 3 equals 0. And we'll take each of these equations separately and solve for x. In both cases, we'll move the constant to the right-hand side. And here I'm going to divide by 2 so that I get x equals negative 1/2, or x equals 3. Those are my solutions. And this is my solution set. Now, before we go any further, I just want to give you a heads up as to a mistake that we might make. And I'm mentioning this because I see some of my students in my calculus classes do this. I don't know why they think this would work. I'm sure they were not taught to do things this way. But I want to give you a heads up as to what I see as a common mistake in my calculus classes. So what I think we might do right now is just nip this at the bud and make sure that we don't make the same kind of mistake. Here's something we want to remember. The zero factor property or the zero product property states that if the product of two factors equals 0, then one of the factors must be 0. So if we have this, the product of two factors equals 0, then either x equals 0 or y equals 0. That's what the zero factor property or the zero product property tells us. So far, so good. Here's the heads up that I want us all to remember. This property is not true for any real number other than 0. So in other words, it's not the case, for example, if we have the product of two factors equal to 1, then one of those two factors must be equal to 1. This claim only is true if the product is 0. And just as a case in point, let's look at something that I might occasionally see some of my calculus students doing. I don't know where they got the idea that they can do this, but when we get to calculus, we'll know not to make the kind of mistake that I'm about to make. Here's what I see some people do. I'll move the constant term to the right. No problem there. That's a legal step. And then they'll factor the left-hand side. There's nothing illegal about what I've done so far. I have the right to add 1 to both sides to get this form of the equation. I have the right to factor the expression on the left-hand side. So nothing wrong so far. But here's the mistake that we don't ever want to make. And I see some people get to this point and then they say, x times x plus 3 equals 1. So that must mean that either the first factor is equal to 1 or the second factor is equal to 1. And then they say, okay, so that means x equals 1 or x equals negative 3. And they're dead wrong. Not only are they wrong when they do this, but after I finish grading their paper, they're dead. They are dead wrong to do this. This is the step that is illegal, immoral, and anything else, any other adjective that we want to attach to it. This is the problem. In the previous step, we have x times x plus 3 equals 1. We have the product of two things, product of two factors equal 1. We cannot assume that either the first factor equals 1 or the second factor equals 1. The only time we can employ that kind of reasoning is if we have the product of two factors that equals 0. If we have the product of two factors that equals 0, then yes, we can say either the first factor is 0 or the second factor is 0. We can't employ that same kind of reasoning if we have the product of two factors equal to any other real number. It may be tempting for us to do, but it doesn't work. There's no such thing called the one factor property, which says that if we multiply two factors together and get 1, either the first factor has to be 1 or the second factor has to be 1. There ain't no such property. The reason this property has a name, the zero factor property, is because it's so special. It only works for one real number, and that's 0. If we have the product of two factors equaling 0, then yes, one of the factors must be 0. We can't say that if we have the product of two factors equal to 1. We can't say that if we have the product of two factors equal to 3 or any other number. It only works if we have the product of two factors equal to 0. So this is a landmine. It's a buried landmine. It's in our path somewhere up in the future. But now that you know what the landmine is and what it looks like, you can avoid it. And I'm telling you this because I see this mistake often enough that we need to be alerted not to do it. If other people want to step on that landmine and make that mistake, okay, let them. But it's not going to be me, and it's not going to be you. Excuse me, if there are any English majors there, I apologize if I've offended you. It is not going to be I, and it is not going to be you. We are not going to make this mistake. We know better. This is pretty much the last of our cases. ax squared plus bx plus c equals 0. And the squared term is not 0. The x term is not 0. The constant term is not 0. And the left-hand side can't be factored, or at least it can't easily be factored. So in that case, we have something called the quadratic formula. Here's an example for us to use the quadratic formula. Here's the quadratic formula. And before I forget, let me stress that this should be memorized. Review it 5 or 10 times a day for about a week, we'll know it for the rest of our lives. X equals quotient on top, negative b plus or minus the square root of b squared minus 4ac all over 2a. Go through it 10 times a day. In about a week, we'll know it for the rest of our lives. Now this thing, I don't think we can factor it. I've looked at it. I don't really see how to factor it. So I'm pretty sure the only way that we can really solve that equation is to use the quadratic formula. By the way, the quadratic formula gives us the solution to this equation. We see an a here and we see an a there. What is a? A is the coefficient of x squared. We see a b here and we see a b here. What's b? B is the coefficient of x in the equation that we're trying to solve. And we see a c here. What is c? C is the constant term in the equation that we're trying to solve. So let's analyze this in terms of a, b, and c. Now, coefficient of x squared, I don't see one. So really, what this is 1 x squared. And when we have 1 times something, we usually don't write the 1. But that's really what this is. X squared is 1 times x squared. So that tells us a equals 1. Now, in our model of a quadratic equation, we have plus b times x. So here we have plus negative 6x. So b is negative 6. And then our constant term, c equals 1. So let's take a, b, and c and plug them into this equation and see what kind of a solution we get. The quadratic formula says that we get x equals negative b plus or minus the square root of b squared minus 4ac, all under the radical, and everything above 2a. So we just take these values for a, b, and c and plug them into that formula. B is negative 6, so we have negative b plus or minus square root of b squared. B is negative 6 minus 4a. A is 1. C is 1. And the whole thing is over 2 times a, and a is 1. This is going to give us our solutions to the quadratic equation. So this becomes 6 plus or minus the square root of negative 6 squared, that's 36, minus 4 times 1 times 1, that's minus 4, all over 2 times 1. (36 minus 4 is 32). Ew. This is not a perfect square. No wonder this equation was something that we couldn't factor. Can I simplify this? Let's see. 32 is 16 times 2, isn't it? We have the square root of two non-negative numbers. We can rewrite that as the product of the two square roots. And this is the square root of a perfect square, 16. So we have 6 plus or minus square root of 16 is 4. Square root of 2 all over 2. And we can divide the bottom by 2, provided that we divide every term of the numerator by 2. This gives us two solutions. X equals 3 minus 2 square root of 2. And it gives us 3 plus 2 square root of 2. 3 plus 2 square root of 2, excuse me. There, that looks a little better. So here's our solution set. And notice that we got two solutions to this quadratic equation. Generally speaking, when we have a quadratic equation, we expect to get two solutions. And I'll talk a little bit more about that in just a second. Let me just note, generally speaking, we expect to get two distinct solutions to a quadratic equation. And this is because if we factor the left side of the equation, ax squared plus bx plus c equals 0, we expect to get something like this. A, which is a constant, times x plus k1, x plus k2, A is a constant. It can't be 0. But one of these two factors has to be 0. If this factor is 0, we get x equals negative k1. If this factor is 0, we get x equals negative k2. And those are our two solutions. So generally speaking, we expect to get two solutions for a quadratic equation. And let's illustrate this with a simple application of the quadratic formula in solving a quadratic equation. Case in point, let's solve this using the quadratic formula. The quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac, everything over 2a. And now we just have to plug in for a, b, and c. A is the coefficient of x squared, so a equals 6. B is the coefficient of x, so b is negative 6. And c is the constant term, negative 36. Holy moly, we're going to have some big numbers here. That's okay, we're up to the task. Negative b, and b is negative 6, so that's negative 6 plus or minus the square root. And the first thing we have is b squared, so that's negative 6 squared minus 4 times a, and a is 6, times c, and c is negative 36. Holy moly. All over 2 times a, where a is 6. Here we have minus times minus is plus. Oh my goodness, let's see. Let me see. I'll just crunch the numbers out. 4 times 6 is 24, times 36. Okay, 6 times 4 is 24, carry the 2. 6 times 2 is 12, plus 2 is 14. Looks good so far. Okay, now 3 times 4 is 12, carry the 1. 3 times 2 is 6, plus 1 is 72. Wow, is this right? Let me see. No, it is not right. I cannot add, can I? 4 times 2 is 6. Okay, that looks right to me. plus 864. Oh my goodness. Oh, wow. Wow, wow, wow. If we add 36 to 864, that gives us 900, a perfect square. Oh, that's great. Over 12. 900. That's 30 squared. So we're going to get 6 plus or minus 30 over 12. So let's see, we can divide, well, let's take 6 over 12 plus or minus 30 over 12. And what do we have? 1/2 plus or minus 5/2. 1/2 minus 5/2 is -4/2 or -2. 1/2 plus 5/2 is 6/2, which is 3. Okay, we got two solutions, just like I said we expect to get. Now let's take this same equation and solve it by factoring to see why it is that we were pretty sure we were going to get two distinct solutions, okay? Here's what we get solving by using the quadratic formula. I'm going to leave this up here, but we're going to solve this equation again by factoring. Let's solve this thing by factoring. If we factor, and I think this is the way that it factors. 2x times 3x is 6x squared. That looks good. And I think the way this factors, and this would involve some trial and error on our part, but I think the way that this factors is +4 and -9. I think that's how it works out. Let's check. 4 times 3x is 12x plus, and 2x times -9 is -18x, and we combine those and we get -6x, 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 okay? This is the correct factoring. And the way we solve this is we use the zero factor property that says if the product of two factors is 0, one of the two factors must be 0. So either 2x plus 4 equals 0, or 3x minus 9 equals 0. And that means that 2x equals -4, or 3x equals 9. And we divide by 2 both sides. We divide by 3 both sides. Oops. We divide by 3 both sides. Okay, we get the same solution by factoring. But notice what's going on when we factor. When we factor the left-hand side of this quadratic equation, we get the product of two factors equal to 0. One of these two factors must be 0 by the zero factor property or the zero product property. If this factor is equal to 0, we get x equal -2. If this factor is 0, we get x equal 3. Two distinct solutions. So in general, when we have a quadratic equation, we expect to get two distinct answers. That's what we expect to get. And the reason is, if we were to solve this thing by factoring, we'd get the product of two factors equal to 0. And that would mean that either the first factor is 0, which gives us the first solution, or the second factor is 0, which gives us the second solution. So in general, we expect to get two solutions when we solve a quadratic equation. In general. Does that always happen? Well, let's see. Let's look at another example. Okay, let's solve this son of a gun using the quadratic formula. So we're going to have x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So we have to identify A, B, and C and plug those jokers into this equation. We have an x squared here, and A is the coefficient of x squared. Well, I don't see a coefficient of x squared. If there's an x squared term here and we don't see a coefficient, that's because the coefficient is 1. This is really 1 times x squared. So our coefficient A equals 1. B is the coefficient of the x term, -6. And C is the constant term, 9. So we have our A, we have our B, we have our C. Let's plug those into the quadratic formula and let the good times roll. -b, b is -6, plus or minus the square root of b squared. B is -6, so we have -6 squared minus 4 times A, and A is 1, times C, C is 9, and we put the whole thing over 2 times A. We plugged in the numbers. Now all we have to do is turn the crank and out pops the answer. So let's do that. Negative and -6 is 6. -6 squared is 36. And 4 times 1 times 9 is 36. Okay, that's what we get. And we have a 0 under the radical. So what we're left with we have one solution. If we've done this right, then we just have one solution, x equals 3. And the fact of the matter is we have done this right, which causes us to wonder, well, if we did this right, if we didn't make any mistakes, why didn't we get two solutions? With a quadratic equation, we expect to get two solutions. And that's true. This is a very special case. And to show why we only get one solution, let's take this same equation and solve it by factoring. If we factor this, we're going to get x here and x here. And we factor 9, and we're either going to get 1 and 9 or 3 and 3. What happens if we get 3 and 3? Does this work? First of all, let's see. Multiplying these two together gives us negative 3x. Multiplying the first and the last together gives us negative 3x. And we add them together and we get negative 6x, which is our middle term. We've done everything right. Our factorization is correct. The factorization is x minus 3 times x minus 3 equals 0. We have the product of two factors equal to 0. The zero factor property or the zero product property tells us one of these two factors has to be 0. So either x minus 3 equals 0 or x minus 3 equals 0. And that gives us x equals 3 or x equals 3. And here's why we only get one solution. When we factored the left-hand side of the equation, the factors were identical. Each factor gives us the same solution, x equals 3. So we end up with one solution. It is possible with a quadratic equation to get exactly one solution. It's a very special case, and that happens when the left-hand side is a perfect square. You see I have x minus 3 here. X minus 3 times x minus 3. That's the same thing, isn't it, as x minus 3 squared. And when we set this factor to 0, we just get one root. So it is possible to get exactly one root with a quadratic equation. Generally, we don't expect that to happen, but it can. And when that does happen, it happens because when we factor the quadratic equation into two factors, each factor is exactly the same. And so when we get a single solution to our quadratic equation, our book calls this a double root or a double solution. In math, sometimes we use the word root instead of solution. But this is the case where we can get a single solution for a quadratic equation. We get a double root or a double solution. See that? Because the quadratic equation factors into two factors that are identical. And so this factor and this factor are going to give us exactly the same solution or exactly the same root. We get x equal 3 from this factor. We get x equal 3 from this factor. We have two factors that give us the same root. So we say that 3 is a double solution or a double root because it's the root of this factor and it's the root of that factor. Well, are there any other surprises lurking in the shadows? Maybe one more. We could have something like this. Looks harmful enough at first glance, but let's try to solve it using the quadratic formula. The quadratic formula says that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So we have to identify a, b, and c. A is the coefficient of the x squared term, so a equals 2. B is the coefficient of the x term, so b equals 4. And c is the constant term, c equals 1 in this case. So let's plug these things in and see what happens. Negative b, b is 4, so this is negative 4, plus or minus the square root of b squared, so that's 4 squared. And you know what? Never mind. This isn't the example I wanted to use. I apologize. I should have thought that out better. We'll solve this using the quadratic formula. And just look at one other case that might pop up. We have x equals negative b plus or minus the square root of 4ac, no, plus or minus the square root of b squared minus 4ac all over 2a. And we just have to figure out what a, b, and c are. A is the coefficient of x squared, so a equals 2. B is the coefficient of x, so b equals 2. And c is the constant term. So let's plug these things into our example. Negative b, that's negative 2, plus or minus b squared, so that's 2 squared, minus 4ac, a is 2, and c is 1, all over 2a. Something look wrong about that? I'm supposed to have negative b, looks good, plus or minus b squared, b is 2. Wait a minute, where's my squared here? There. Why didn't you people tell me about, don't let me make a mistake. When I make a mistake, speak up and I'll gladly correct it, even if you are just watching this as a video. Okay, now we're good to go. B squared, that's 4, minus 4 times 2 times 1 is minus 8. All over 2a, and a is 2, so this is, let me put 2 in here for a. 2a, 2a. Things look okay so far. 4 minus 8, negative 4. And all of a sudden, that we have problems. The square root of negative 4 is not a real number. If we're looking for real number solutions, we ain't gonna get none. We ain't gonna get none. As soon as we get a negative under the radical, when we simplify everything under the radical and it's negative, we know that we're not going to get any real number solutions. And if we're writing the solution set, I guess we'd write it like this. The set containing no elements, the empty set. This would be our solution set. In general, we expect to get 2 solutions to a quadratic equation. On rare occasions, we'll get just 1. And also on some rare occasions, we'll get none. Typically, we expect to get 2, but whatever appears under the radical will determine how many solutions we get. And you know what? That's a good retrospective. Let's revisit all of the examples that we did, and we'll notice what happened in every case where we had 2 solutions. We'll notice what happened in the case where we had exactly 1 solution. And we'll notice what happens in the case where we have no solutions. So let's summarize that. Okay, how many solutions do we expect to get to this quadratic equation? We're going to get 2 solutions if the expression under the radical, once we simplify it, turns out to be a positive number. So if we get a positive number under the radical, we're going to get two solutions. And that's the same thing as saying that the contents of the radical, b squared minus 4ac, is positive. When do we get exactly one solution to a quadratic equation? Think about it. In the example that we had where we got one solution, we had a 0 under the radical. If, when we simplify under the radical completely, we get a 0, we're going to get one solution. And when do we get 0 solutions? If, when we simplify under the radical, we get a negative number, that means there are no real solutions. And I better cover my fanny here and be a little bit more specific. How many real number solutions? If there's a positive under the radical, we get two real solutions. If there's a 0 under the radical, we get one solution. If there's a negative under the radical, we get 0 solutions. Now, our book explains this a little bit differently. But this is the easy way to remember it. Positive expression under the radical, two distinct solutions. 0 under the radical, one solution. Negative number under the radical, 0 real solutions. Our book actually gives a name to something. It calls the expression b squared minus 4ac the discriminant and I guess they call this thing the discriminant because it distinguishes the three cases. The discriminant, if it's positive, we have two real solutions. The discriminant, if it's 0, one real solution. The discriminant, if it's negative, 0 real solutions. So b squared minus 4ac, and that's the contents of the radical, b squared minus 4ac. So if this thing is positive, two solutions. If the discriminant is negative, if the discriminant is 0, we get one real solution. And if the discriminant is negative, we have 0 real solutions. Now there's one other thing that I have to cover. Apparently we're going to need this. If we take calculus, we'll need it a little bit in Cal 2. We may need this in other areas also. It's called completing the square. This may seem like a rather crazy thing to ask, but if we take x plus a number and square it, what does it look like? What form does it have? Well, let's multiply it out and see, okay? And we do first, we do the outer, then we do the inner, and then we do the last. If we square x plus a number, it's going to have this form. And notice, no, it's not either. Oh my goodness. Okay, this looks much better. Holy moly, I need to pay attention. Now we want to analyze this form closely. Now here's what I claim. This thing is going to be 1/2 the coefficient of x squared. Now, what is 1/2 the coefficient of x? Here's x. The coefficient of x is 2k. So, 1/2 times the coefficient of x is going to be 1/2 times 2k. And then we square it. So if we take x plus a number and square it, this is what we get. And the relationship between the constant term and the x term is that the constant term is 1/2 times the coefficient of x squared. Let's see if that works with an example or two. Okay, here's our example. X plus 3 quantity squared. And we take the first, x squared. We take the outers, 3x. We take the inners, 3x. And we take the last, 3 squared, which is 9. And that's equal to x squared plus 6x plus 9. Now, what we observed previously is that the constant term is going to be 1/2 the coefficient of x squared. Does that work? Let's see. Is it 1/2 times the coefficient of x? This is the coefficient of x, 6. Squared, let's see, 1/2 times 6 is 3. It works. Now let's try a little bit more complicated example. Okay, let's take this expression, x squared plus 8x. What number would we have to add to this expression in order to make it a perfect square, something in the form of x plus k squared? we know what this is supposed to look like. This number is supposed to be 1/2 the coefficient of x squared. So what's the coefficient of x? It's 8. 1/2 the coefficient of 8, 1/2 the coefficient of x, 1/2 8, quantity squared. So that's 4 squared, or 16. Now let's check. If this is a perfect square, then the number that we put here should be the square root of 16, the square root of this number. Does it work? If we multiply this out, we're going to get x squared. We're going to get 4 squared is 16. And we're going to get 4 times x doubled is 8x. That works. Or if we want to FOIL it out, we'll get x plus 4, x plus 4. And we'll take the first plus the outers, 4x, plus the inners, 4x, plus the last 16, okay, it worked. Now, why do I want to do something like this? That we'll see in a few minutes. Let's do another one just like this. This one's a little bit more complicated. What number do we need to add to x squared plus 5x? To make it a perfect square, that is in the form of x plus k squared, here's what we do. If this really is of the form x plus k squared, then what goes here is 1/2 the coefficient of x squared. So it should be 1/2 times 5 squared. And let's see, what is that? 1/2 times 5 squared, that's 5/2 squared, which is 25 over 4. Okay. X squared plus 5x plus 25 fourths and that supposedly will be x plus some number squared. And the number that goes here is the square root of 25 fourths, 5/2. Now, does it work? Let's check. We'll do the outers. Whoops. We'll do the first. X times x is x squared. We'll do the outers. X times 5 halves is 5 halves x. We'll do the inners. X times 5 halves is 5 halves x. And 5 halves times 5 halves is 25 fourths. Okay, that's exactly what we should get. So x plus 5 halves squared does equal this thing. Let's do one more example. Okay, what number do we need to add to this thing to make it a perfect square? We take x squared minus 2x plus, and we're going to stick with our formula, 1/2 times the coefficient of x squared, 1/2 times the coefficient of x squared. Now let's see, what is that? 1/2, the coefficient of x is -2, and we square it. Okay, we get -2 times 1/2 is -1, and we square it, we get +1. And does that work? Yes, it does. Now let's see, this should be x plus or minus something. Since we have a minus here, it's going to be x minus something squared. And it's going to be the square root of this thing doubled. The square root is 1. We're going to double it. That's going, no. Oh, I'm being stupid. Since this is a minus, this will be a minus. And what goes here will just be the square root of this number. Forgive me, it's been a long lecture. Now, why do I care about this? I'll tell you in just a bit. Let's look at a couple of examples, and that will sort of clue us in as to why we care about taking x squared plus something times x and turning it into a perfect square. How would we solve this for x? Well, let's see. I'd like to get x by itself, so the first thing that I'll do is compute the square root of both sides. And when I compute the square root of 16, I'll get the positive root and the negative root. Oh my goodness. Now all I do is subtract 3 from both sides. Negative 3 minus 4 is negative 7. Negative 3 plus 4 is 1. Those are our solutions. Now let me just check. I'll take each of these and plug them into the original expression. So let's see. X plus 3 squared, that's negative 7 plus 3 squared equals 16. Let's see. Negative 7 plus 3 is negative 4. Yep, that works. Now let's try this one, x equals 1. I'll take x equals 1 and I'll plug it into this equation. 1 plus 3 squared equals 16. Let's see. 1 plus 3 is 4 squared equals 16. Yep, it works. Okay, so we did that right. Let's do one more like this and I'll let the cat out of the bag. Here we go. Solve this for x. Well, to isolate x, the first thing I'm going to do is compute the square root of both sides. And I'll get x minus 2 equals square root of 9 plus or minus. Oh, wow. Just add 2 to both sides, right? 2 plus or minus 3. So x equals 2 minus 3 is negative 1. X equal 2 plus 3 is 5. And mentally, let's just check both of these. If I take negative 1 and plug it in for x, I get negative 1 minus 2 is negative 3 squared is 9. Yep, that works. If I take 5 and plug it in for x, I have 5 minus 2 is 3 squared equals 9. Okay, it worked. Now we're going to cut to the chase. We're going to solve quadratic equations again, specifically this quadratic equation, doing something called completing the square. And here's how we do it. First thing we do, take this constant term and move it to the right side. Why? You'll see in just a minute. The next thing that we do is transform the no, it's not the next thing that we do. Forgive me. Oh. The next thing we do is divide by the coefficient of x squared. So we have the coefficient of x squared now equal to 1, and we have the constant term on the right side of the equation. And now transform the left side into a perfect square. And what do we have here? We have 1/2 the coefficient of x quantity squared. So we take 1/2 of the coefficient of x, which is -5/2, and we square it. Well, if we do that to the left side, we're going to have to do it to the right side also. And by the way, from work we did about 10 minutes ago, we know that the left-hand side is now a perfect square. So just as a note, we call this step completing the square. In other words, we make the left-hand side a perfect square. And I think I'm going to want to simplify this before I do anything else. So let's see what we got. X squared minus 5/2 x plus -5/4 squared (3/2) plus -5/4 squared and let's see, we should get 25/16. I'm going to rewrite the left side as a perfect square. So I'm going to get x, and since this is a minus sign, I'm going to get minus something squared. And what is it that goes here? It's the square root of that thing, 5/4. And on the right side, holy moly, let's see, 3/2 is the same as, well, let's see, multiply top and bottom by 8. So I should get 24/16 plus 25/16, 49/16, okay. And let me erase some of the board here. Okay, rewrite is a perfect square. And now solve for x. So we compute the square root of both sides. And we get plus or minus 7/4. And then we just add 5/4 to both sides. Five-fourths minus 7/4, and that's what, -2/4, which equals -1/2. So that's one solution. And we also get 5/4 plus 7/4, which equals 12/4, which equals 3. Oh, and I guess we're obligated to check our answers. So let's do that. If I'm not mistaken, I think the original equation was 2x squared minus 5x plus 3 equals, let's see, minus 3. Is that right? Minus 3 equals 0. Let's try this one first. It's easier. X equals 3. 2 times 3 squared minus 5 times 3 minus 3. So let's see. 3 squared is 9. So this is 18 minus 15 minus 3 equals 0. Okay, check. That works. X equals -1/2. 2 times -1/2 squared minus 5 times -1/2 minus 3 equals 0. Let's see. 1/2 squared is 1/4 times 2 is 1/2. Negative times negative is plus, so that's 5/2. 1/2 plus 5/2 is 6/2, which is 3. Minus 3 is 0. Okay, check, it works. Well, I'll tell you what, that was kind of a nasty example. Let's do another one. One more example. This is a little bit nicer than the last one. But we're going to complete the square. So the first thing we do, we move the constant term to the right side. Now the next term. Do you remember what the next term was? In the last example, I almost forgot to do it. Divide by the coefficient of x. X squared. Divide by the coefficient of x squared. Whoops, 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 whoops. Okay. The next term is called completing the square. And this is where we transform the left side into a perfect square. And we take 1/2 times the coefficient of x and we square it. The coefficient of x is -1. So we take 1/2 times -1 and we square it. And we add it to both sides. And now I guess I'm going to simplify this mess. (1/2) times -1 is -1/2. Ooh, we got to convert this to fourths. Let's see, 6 is okay, 25/4. That's what that mess is. And now I'm ready to do step 4. Express the left side as a perfect square. So we're going to have x, and because this is a minus, We're going to have a minus sign. And we're going to do the square root of this thing, which is 1/2. I might also add that whatever number appears in here, whatever number we actually end up squaring, is the number that goes here. So if we see a negative 1/2 here, we have a negative 1/2 here. That's another way of looking at it. And on the right, we have 25/4. Okay, here comes the good part. Solve for x. We compute the square root of both sides. And the square root of 25/4 is plus or minus 5/2. And then we just add 1/2 to both sides. Whoops. So x equals 1/2 minus 5/2. So that's negative 4/2, which equals negative 2. Or x equals 1/2 plus 5/2. Which is 6/2, which equals 3. And I guess we're obligated to check this, aren't we? Just in case we've made a little mistake. Now, our original equation, 2x squared, and let's see, 2x minus 12, I think that's what it was. I hope that's what it was. X equals negative 2, let's try that. 2 times negative 2 squared minus 2 times negative 2. Minus 12 equals, let's see. Negative 2 squared is 4 times 2 is 8. Negative 2 times negative 2 is plus 4. Minus 12 is 0. That checks, okay? Well, the first solution worked, so that's a good sign. Now let's try the next one. X equals 3. 2x squared minus 2x minus 12 equals 0, we hope. And this is 6. Whoops, whoops, whoops. I do not like where this is. Oh, my goodness. 2x squared. Holy moly. So this is 2 times 9 is 18. Minus 6 minus 12 equals 0. Check. Okay. There are better ways to solve a quadratic equation than using completing the square. We learn this method in part because we can do other things with the completing the square technique other than just solving quadratic equations. In Calculus 2, there are going to be some cases where we have to use completing the square technique, and it has nothing to do with solving a quadratic equation. So Completing the square, not the best way to solve a quadratic equation. But if we learn how to solve a quadratic equation this way by completing the square, if we get into calculus 2, and some of us will, even though we don't think we will, some of us will end up in Cal 2. And we're going to need it to do things that have absolutely nothing to do with quadratic equations. So the bottom line is learn this stuff, and when you end up in Cal 2, contrary to what your plans are right now, you'll be well prepared.